Hello, and welcome to today's Offshore Magazine webcast, Accelerate Your Offshore Structural Analysis by 10 Times, sponsored by MSC Software. I'm J.B. Avance, your moderator. Thanks so much for joining us. Before we begin, just a couple of webcast housekeeping items. This presentation is live and interactive, so you may ask questions at any time by clicking the Ask a Question box in the presentation window, then clicking the Submit button. If you are running pop-up blocking software, you will need to disable it to view this webcast. In addition, it is recommended you close down all other applications for best performance. For your convenience, this presentation will be available on demand within 24 hours. A reminder email message will be sent with a link to the archive. It will also be accessible from the home page at www.offshore-mag.com. If you would like to download a PDF copy of today's slide presentation, you may do so by clicking on the Event Resources tab on your webcast console. Now allow me to introduce today's presenters. Fred Harvey is MSC Software Manager, Oil and Gas Solutions. He received his mechanical engineering bachelor's degree from the United States Naval Academy in 2003. Fred spent the next 10 years as a Marine Corps helicopter pilot and officer in charge of several teams, including administration, intelligence, operations, and logistics. Fred joined MSC Software in 2013. He is managing development and application of MSC technology for innovative oil and gas industry solutions. Our second presenter is James Pura, MSC Software Application Engineer. He received his mechanical engineering bachelor's degree from the University of California, San Diego, specializing in structural analysis. James has worked for a number of companies with broad finite element analysis applications, including Boeing, Space Exploration Technologies, SpaceX, and NASA Jet Propulsion Laboratory. Before joining MSC Software, James was a structural dynamics testing and FEA expert for Altair Engineering, working with customers to optimize their FEA workflows in oil and gas, automotive, consumer electronics, heavy industry, and aerospace. James has been with MSC Software for 4 years, specializing in the application of finite element analysis. He works specifically as an application engineer specializing in the next generation platform, MSC Apex. And now it's my pleasure to introduce Mr. Harvey.
Thank you, JB. Good morning, and thank you for joining our webinar on offshore structural analysis with MSC Apex. I manage a team that essentially builds out simulation solutions for the oil and gas industry that is leveraging MSC's technologies that are widely best in class and heavily used in other industries and very applicable to similar challenges in the oil and gas industry. So today I will start out by providing a brief introduction to MSC Software for those of you who may not be familiar with our company, and I'll summarize the purpose of today's webinar. James will introduce MSC Apex and provide some context around this paradigm shift that Apex brings to structural analysis as compared to other traditional methods. He's going to offer 3 short demos. The first demo will show how the use of scripting can fully automate building a model for large assemblies. When you think about large assemblies, many models like ships, hull structures, other offshore structures are very similar in the modeling process. That process can be identical except for various design parameters, small changes. So the scripted approach is very applicable to these redundant processes and significantly cuts down the modeling time and simulation time. In many cases, some designs are unique or one-off. They don't necessarily fit into the scope of a particular script. So the second demo shows an efficient workflow for manually building a jacket model that might represent such a one-off design. The third demo will show how scripting can be utilized again, but this time to automate a small subset of repetitive tasks. Even for these one-off type models like the jacket, parts of the process like modeling fasteners or defeaturing specific geometries can be automated and make a tremendous amount of work very easy and efficient. And so we're hoping that you'll notice that the amount of work done in these demos is quite an astonishing amount of work to be done in the time frame of 30 to 40 minutes of the webinar. So that brings me to who we are and how we got here. MSC Software was founded in the early 60s by a couple engineers. These are folks that pioneered the early finite element analysis approach using computers. They developed the first commercially available structural analysis software, and soon after won a contract with NASA to develop Nastran, which is NASA structural analysis. And to this day, still sets the bar for high-end simulation structural analysis software, and it's the de facto standard for structural analysis in aerospace and automotive industries. I'm not going to go into details on this slide, but I do want to offer the information to glance over. But I do want to point out that for that 50 years to follow, from the 60s to now, MSC has continued this trend of innovation in the computer-aided engineering industry and maintains a very broad portfolio of best-in-class tools that cover a wide range of physics and simulation methods. This is what we do. Our world is simulation, computer-aided engineering, so we are very good at it, and that's essentially our legacy and what we continue to bring to the table. Almost all major auto, aero, and heavy machinery manufacturers are our current customers, and our top 50 customers have been with us for over 25 years. And I think it's just a testament to our commitment to simulating reality and capturing the right physics and delivering a level of certainty that builds an unmatched confidence and trust in simulation results for our customers. So we continue this legacy of innovation with the release of the MSC Apex, which is what we're here to show you today. And this is the latest technology developed for structural analysis. With that, I'd like to hand over to James Pura for an introduction to MSC Apex.
Thanks, Fred. And just to build off of what Fred said on that last slide is that there is no problem too difficult for MSC software. We never shy away from difficult problems, which is part of the reason why we have that 25-year partnership with all of those major OEM customers. And we would like to continue that partnership with a lot of you today. So please, if you like what you see today, please don't hesitate to reach out, and there is no problem too difficult for us. So let's lighten up the subject a little bit. Why should you care? I realize that this webinar today is on a Monday morning, and our competitive landscape for this is that you could be drinking coffee, you could be checking emails, or you could be doing basically anything else that is more fun than sitting here and watching our webinar. So we realize that your time is valuable, and our promise today is that the presentation will be more fun than at least 2 of these options, maybe even 3. I'm not sure. It might be overstepping our bounds there, but still, if it applies to you, I hope you enjoy it. And we have designed this presentation to really engage your specific workflows for offshore structures. So let's take a step back through time and let's see how we actually got here. So this is the evolution of all finite element analysis in one PowerPoint slide. So you can see that this entire industry got started back in the 60s when our company, MSC Software, actually partnered with NASA in order to develop this thing called, a computer and software, back when the term software was still being defined by Webster in the dictionaries, right? So we were still trying to figure out what this actually was going to do, and here we are over 50 years later, and the industry has become somewhat stagnant. A lot of the tools that you're using today, including ours, you look at them and you say, it feels like I'm in a Windows 95 environment. There's no copy and paste. There's no drag and drop. There's no modern user interface. And though our tools were really our workhorses, right? You could go off and use MSC Nastran to design and build an international space station that stays in space in orbit for 20 years. And that's okay. You can do that. Again, we don't shy away from the difficult problems. But it still doesn't take away from the fact that these tools were built 30 to 40 years ago, and they're built on an architecture that is not modern. And so we realized this about 10 years ago. And we looked at it and we said, look, our customers love us for the answers that come out of our software and our tools. Human lives depend on the answers that come out of our tools, and we don't take that lightly, right? But we do want to leverage the fact that everybody has a laptop with multiple parallel processors on their computer, on their desk now. right? That's something that didn't exist back when CSAM and SACS was first being developed. Back when this whole computational fluid dynamics thing didn't even exist because computers weren't even capable of handling that much memory and hard drive space. Back when computers would fill up the room sometimes, that's the kind of structural analysis that these platforms were built on back in the 70s and 80s. Well, here we are in the 2010s, and MSC Software leadership, we realized that we needed to do something new for the next generation of structural analysts. Now, this doesn't mean that this is a tool just specifically for those kids coming out of college. Definitely not. We wanted to develop a tool that the 20, 30, 40-year finite element analysis guru would really jump towards MSC Apex as well. And that's a very fine line to make sure that you develop a tool that gives homage to the legacy of finite element analysis and gives you all the bells and whistles and the answers at the end of the day that customers trust and rely upon and human lives depend on, but also modernize it, right? Give you a user interface that really matters. Do modern user interface type stuff like copy and paste and all that good stuff. So what we did is that was the impetus to a worldwide trend, a trend survey. And so we went out to our customers. You know, we've got Ferrari in Italy, we've got Honda, Toyota in the Far East, we've got NASA, Airbus, Boeing. All these guys have been using our tools for 25 plus years, and we said, all right, you guys, in 13 different languages, tell us basically two things. Tell us what you like about our software and what we should keep, and tell us if you were, as a user, to create a wish list of what the best possible finite element analysis software would be. No matter how crazy it is, tell us what it looks like and how it works, and we'll do our best to build it. And sure enough, we got it was a very passionate response in about 13, 14 different languages worldwide. And we used that as our prioritized to-do list for MSC Apex. And that was about 10 years ago when we first started this project. Now, it took us a few years to actually write a single line of code. It took us 2 years to just sit down and figure out what that prioritized list looks like. And two of the biggest things, number one and number two, which is going to be the main focus for the demonstrations today, is on the left, you can see a list of CAD-related, pre-processing related stuff. And then on the right, you'll see challenges that came with finite element analysis. And on the left, it's just things like that my CAD looks great in the CAD software, but when I start doing a structural analysis, I need to get rid of things like holes and fillets and weld lines and all this stuff. And a lot of time I have CAD geometry that just is not analysis suitable, and I need to somehow bridge that gap. And please fix that for me. The other thing on the left-hand side was that geometry pair and meshing operations are tedious, they're error-prone, and it takes far too long. One of the things that we heard the most from in all sorts of parts of the world were engineering managers complaining to us saying, I hire engineers to be engineers, not to be modelers, right? If I hire my engineers and 75% of their work is spent tinkering around with translating CAD software into something analysis suitable and figuring out how to get a right mesh and how to connect these surfaces and how to trim surfaces and how to translate it to a different file structure, that's not engineering, right? Engineering is looking at your structure and saying, okay, based on my experience, based on the answers coming out of the software, based on my personal engineering intuition, I can sign off on this design because I believe it is structurally worthy of the load that it's going to take, and let's move forward with manufacturing it. Now on the right, we heard challenges as well regarding the finite element analysis process itself. Things like the analysis input deck creation, it's tedious, it's error prone, and it takes too long. And then something else that came from the younger generation, which is, why is it that I have to edit a text file, right? Whenever I want to change my analysis input deck. That feels like 1950s, 1960s to me. And so we said, okay, you know what? We can address that. We can still give the engineer that option, but let's not make it required for every single analysis, okay? So if you want it, it's there. It's like a warm, comfy blanket. It's sitting on the couch whenever you want it, but you don't need it for every single workflow, right? And then the other thing is that incremental changes require complete reruns of systems. Like, let's say you're the engineer responsible for validating a design, and you're looking at this analysis and you're saying, you know what, it's just not up to the load that we're designing it for. And my engineering intuition says that you need to stiffen up this part of the structure and change the design here and do this and do that. It's almost there, but you need to do a little bit. Now, in any other tool other than Apex, you would have to go right back to CAD. You would have to export a brand new CAD geometry file and then basically start over with your finite analysis. And that was a problem, right? And so we knew that we needed to address that as well, because incremental changes should require incremental amounts of time to make the change, right? It shouldn't require a complete rerun of the system. So where did we end up? Well, after all those surveys were prioritized and looked at, we said, okay, let's rethink this entire interaction of the process. We have a pivotal moment here at MSC because we're developing a pre-processor, a post-processor, and a solver all at the same time from scratch, which has honestly never been done before in this industry. If you look at the history, it's been piecemeal, right? Company A acquires company B and then tries to develop it into a full platform and, you know, prices it accordingly. Or somebody goes out and buys another company and tries and puts a GUI on it, tries and makes it part of the platform, stuff like that. And we are just as guilty of that as everybody else in this industry. And so we said, look, if we're going to invest this amount of money and this amount of time to develop something, let's make it paradigm shifting. Let's really make it worthwhile. And one of those things is this wash, rinse, repeat cycle of pre-processing, solving, post-processing, getting an error, going back to pre-processing, fixing that error, and then solving, crossing your fingers, and then getting a different error, and then going back and fixing it, and on and on and on. We said, all right, let's fix this. Let's get it to where we reach that holy grail of finite element analysis, which is you push solve once and you get answers once. And not only that, but you get the answers that you hope for and you're expecting. Okay, and that's really what Apex is. The moment you bring in CAD into Apex, it automatically knows the location of every hole, every line, every fillet, every surface, everything. And it knows the dimensions of everything, which makes it completely generative. The moment you assign a mesh to it, the mesh optimizes for the geometry, again, without you even having to do anything with it, right? And these are the things that you can leverage modern day computing for. Now, this is not our first release that we've had. We have been waiting for the product to get to a maturity level where we could really reach out to the oil and gas and offshore industry and say, you know what, if you build a large fabricated structure, this is the tool for you. And sure enough, now we are there, and hence why we're giving you this webinar today. The beginnings were really that modeling and meshing portion, that really big pain point of, you know, I'm paying my engineers to do engineering, not modeling. That was the first couple of releases that we focused on that. And even within that, we focused on the 2D mid-surfacing and meshing, shell meshing workflow. The next complaint that we addressed over the course of 3 releases was, all right, why am I paying my engineers to do a basic linear static or normal modes analysis and it takes weeks? How can you turn that down to hours or at the most a day or 2? And we said, okay, you know what, we could do that too. And sure enough, we did. And so here we are now that we have an entire suite of analysis tools capable for you. We have linear dynamics, we have linear buckling, we have interoperability with Nastran, and we have composites, we have orthotropic materials, basically anything you would need for a large fabricated structure we have. So what is Apex Modeler? Apex Modeler is the CAD to mesh solution. This is the pre-processing standpoint. We license it two different ways. We have Apex Modeler and Apex Structures, so it's a little bit cheaper if you just do the pre-processing portion of it, and then you can move to whatever solver you choose. And that's the other thing, is the fact that we are completely complementary to whatever solution that you have. We're not here today to say, get rid of CSAM or SACS or whatever other tool that you're using today and go with us because, you know, lose the zero, go with the hero. That's not what we're here today to tell you how to do. We are a complementary solution. We are here to speed up your process, and we are here to help you get to the finish line faster. Okay, no matter what that finish line looks like, we can get you there faster than what you have today. okay? But the biggest thing from this slide here, the biggest takeaway here is that Apex is easy to learn, easy to use, natural, and intuitive, okay? 4 things that have traditionally never been associated with finite element software ever before, right? So if there's one takeaway from today's presentation, it's that, it's that James is far too excited about finite element analysis than any other human probably should be. But the second takeaway would probably be those 4 things, okay? Apex is easy to learn, easy to use, natural, and intuitive, okay? So one of those things of being easy to use and easy to learn is the fact that Apex is completely self-taught. Okay, there is no training class associated with Apex. You pick it up, and within hours, you're off and running, and you're picking it up yourself. Me personally, I came from Altair, and I came from the HyperMesh workflow where you took 2 full-day training courses in order to even learn what left mouse button does and right mouse button does. And we said, okay, you know what? Let me put this to the test. Within 4 hours, I was ready to go. And part of that is the fact that we have smart tools. The moment you see the demonstration today, you're going to see the fact that there's a vast majority of tools are gone. They're disappeared because we've integrated that technology into Apex. Now, in the image you're going to see here, what happens when you join those 2 red lines in order to get that fillet connected to that top surface there? That traditionally took 8 different tools in our legacy tool. We said, you know what? Let's throw down the gauntlet here. Let's figure out how to make that faster and easier. And sure enough, we did. In Apex, it's just a drag and drop operation. Okay, so 8 tools down to 1, 10 times reduction in the amount of time necessary. Now, Apex is self-taught. I already told you about that. Now, let's put our money where our mouth is, right? So we went out to our customers worldwide and we said, all right, let's put this to the test. And so here is an audio package. What you're seeing is kind of like a plastic enclosure of 15-inch subwoofers. So you can imagine there's a lot of vibration, a lot of structural loading that goes through this thing. And cracking and consumer product quality is of utmost importance to this customer. And so we said, all right, if you were to build a mid-surface, how long would this take you? Well, for their best engineers, it took 10 hours. In Apex, it took 1 hour. Okay, so there's your 10x return in pre-processing time. Here's another example. Now, this is a machined metal part for one of our customers, where you say, all right, let's get from solid geometry to mid-surface. And this took over a week in their current workflow. And then switching over to Apex, it took less than a day, almost half a day. Okay. Now, you may be thinking, well, what does this pre-solve post workflow look like? Well, we import all the major CAD formats. We also import Nastran legacy bulk data files. But when you're making geometry changes inside of Apex, like you're testing your engineering intuition and whatnot, you can go directly into the bulk data file, or you can spit out your changed CAD format in ASYS, Parasolid, or STL, and you can go right back into your CAD format and do the full loop, right? So let's say you added a rib or changed a fillet or moved a fastener hole or something like that in order to make your structure more, structurally sound. You can go right back into your CAD system and change your drawings and go straight out to the manufacturing floor with that changed design so that you're not locked in within the Apex platform, okay? Now, Apex Structures is that second half of that. That is the solver and post-processor. This is where you really can test out your engineering intuition and really see back-of-the-envelope loads and calculations in a matter of minutes instead of hours or days. Okay. Now, the 4 technologies that we have today available, new stuff is coming out almost every day within the Apex platform, but we have linear static, normal modes, linear buckling, and linear dynamics. Okay, so it's completely integrated in generative, which you'll see part of the demonstration today is going back and changing the design after an analysis has already been done, and we do that on the jacket assembly. Now, computational parts and assemblies allow for that generative and integrated platform to work because you have things like incremental validation and incremental solution. Gone are the days where you have to cross your fingers after you spend weeks of building a model and then hope that your model actually runs, and then going back and spending 2 or 3 days actually just debugging your model so that you have a runnable model. You don't have to do that anymore inside of Apex. And in fact, that was one of the things that we set up from day one to fix, which is you have this incremental validation and incremental solution. And it is so easy that you'll see in the demonstration that you'll really love it, okay? And with that, let's go straight into the demonstration. So for the first demonstration, I'm going to show you a little bit about the Apex platform first before we jump into the actual demo. So the moment you open up the tool, you find this little pop-up window that has over 250 videos built in to every single functionality inside of Apex. Now, the good news is that if you need video number 238, do you have to watch 237 videos first? And the answer is no. So this is really just there for reference. Let's, for example, let's say you wanted to do a 2D representation of a 3D solid, or say a mid-surface, okay? So all you would have to do is hover over the tool, and immediately you get this little synopsis of what the tool does, and you've got this little video icon, and sure enough, you click on it, and right there it brings it directly to the filtered list of videos that are specifically connected to the mid-surfacing workflow. Okay, so there you go, it's right at your fingertips. Now that is for basically everything. Let's assume you want to import some geometry and do some cleanup on it. You have the exact same capability associated with that. And the idea behind this is that you have, at every stage of the game, from the most easy to the most advanced type of analysis workflow, MSC, you basically have an MSC virtual assistant sitting on your shoulder, giving you tips and tricks along the way. At no point should you feel left out in the cold and all by yourself. Now, on to the actual demonstration. Some of you on the call may be Intergraph users. So things like Intergraph Smart 3D, for instance, for a ship or for an offshore structure. Because Intergraph and MSC are both part of the Hexagon family, we've created a synergistic component to that, to where it saves the user time and effort from bringing in their model and repeating themselves by rebuilding the exact same steps that it took to build their CAD model to begin with. So you can skip that stage in your finite element model building process. So what we're going to do here is we're going to actually just play a macro that we've had set up for us that is basically reading in the two-part export from my Intergraph model. I have, and just going through this here, you can see that I have for a section of my part, I've got, if I go to all files, you'll see here that I've got IGES files that have been exported. These are my geometry pieces, and then I've got an XML file that shows me all the metadata associated with those parts, like the cross-sectional area of the beams and all that kind of good stuff. Okay, so if I go back here to the ship Python script, all I would do is it's going to bring in and associate all of that data, so thus saving me time and effort from building it from scratch. And while we wait for this model to work, I'll just kind of narrate and give you the play-by-play. What this is doing is it's creating a section of a ship, and the section is basically in the middle of what you would think of like maybe a freighter ship, something that would carry cargo or something like that. And what you're seeing here are the horizontal surfaces, are the sheet metal sections, and they're stiffened underneath and on the side by 1D beam models. Now, both of those are used heavily in the shipbuilding and oil and gas industries, so this should be very familiar to you in terms of a finite element model build process. Apex excels at both 2D surface meshes and 1D beam meshes, so we thought that this was a great example to start off with and show you that we do both of those workflows. And so I'll just wait for this model to finish, and then we will go on to finishing up the model. And due to the magic of webinars here, we can just skip towards the end here, and you can see that this Python script has successfully executed. I've just saved you the pain and anguish of hearing me tell jokes for the last couple of minutes. The script itself only takes about 1.5 to 2 minutes to complete, and here is your completed ship hull section with 1D beams stiffening up the 2D surfaces.
for both the top and bottom and the sides of the hole. Okay, so now the only steps that are left in this model building process is first we have to mesh it, secondly we have to connect all of these pieces together, and then thirdly we have to assign boundary conditions. Now I'm going to skip that last step just so that we can have enough time to move on to the rest of the demos. But just know that Apex can walk you through every stage of the game, no matter what your boundary conditions are. Now, what I'm going to do is I'm going to turn off the 1D surfaces and the geometry and the beams so that I'm just left with the two-dimensional surfaces. And I'm going to go into that meshing tool that I showed before. And I'm going to assign a mesh of 0.25 meters. And I'm just going to drag a box around the entire thing. And as I interrogate my model and I zoom in a little bit, it looks like I've got a nice clean mesh. Now, if at any point in time I want to check the element quality, I absolutely can. I just go right up here to element quality, and notice I have 0 invalid elements that were created, which are nice, which means it is run ready right off the bat. Now, if I want to see what the bad element locations are, I could do that too. I can right click and I say isolate and enhance. And sure enough, it'll show me exactly where those bad elements are. But again, remember, this is completely optional because it's run ready. Okay? But if I do want to zoom to it, let's say I've rotated my model around and I don't know where it is, it's off the screen, all I have to do is click through the list one at a time, and I can see exactly where they're at and they're located, and I can fix them one at a time. Okay? So we're going to skip this stage, but I just wanted you to see and know that that was there. Okay? Now, if we go back to this, the next stage would be to assign the 1D beam mesh to the surfaces, the 1D lines, not the surfaces. And here you can see that the beam spans have already been assigned to the 1D lines. So I'm going to turn off the beam span just so that we're just left with the geometric lines. And I'm going to go back to the meshing panel, and I'm going to choose 1D curve mesh instead of surface mesh. Thankfully, they're right in the same place. And again, I'm going to use the same mesh size. And I'm just going to drag a box around all of them. Notice right down here in the status bar it created 170 curve meshes, which it also counts the number of elements associated with it. A nice feature of beam meshing inside of Apex is that at every node location you have a cross-sectional fringe plot in post-process. Okay? So the next step is let's bring back our 2D surface mesh. And the next step is to connect all of these together. Now this workflow right here causes considerable anguish for our users, but not anymore inside of Apex because it's nice and easy. Now, before I show you the nice and easy workflow, I wanted to really kind of help you appreciate all the effort that we've gone into this. Now, anybody that's done this kind of mid-surfacing workflow before understands that you really have to connect these one at a time to each of the surfaces and make sure that they're all fully connected, and then you have to make sure that all those T-junctions are correct so that you have coincident nodes along every boundary and all that kind of stuff. You don't have to do that anymore inside of Apex. Not to mention taking all of these surfaces and beams and putting them into their own part file so that it acts as one monolithic surface. You don't have to do that anymore inside of Apex. You can leave it in the assembly structure that you have, okay, and you can keep all of those sections and subsections attached to one another so that you could run each sub-assembly independent of one another inside of Apex due to Apex's solving capabilities. Now, what I'm going to do is I'm going to go to the Connections tab, and or Interactions tab, I'm sorry, and if I go to Edge Ties, I'm going to, again, just drag a box around everything, and it's going to automatically connect all of these pieces together. Now, this is a two-step process. Step one is select all the edges or faces of what you want to connect. And then step two is to select all the faces that you want those faces and edges to connect to. And sure enough, I'll just let Apex just sort it out by selecting everything for both sections, and it'll automatically connect it. Now, as this is running, it is also editing the mesh so that the mesh is coincident, lining up. It's moving each nodal location side by side so that it's nice and connected together. And if I turn on my beam spans again, I can notice that each node location is lining up with the 2D surface meshes, and we are good to go. Okay. All right, so now we are ready to analyze. So the next step is to assign the loads and boundary conditions, and I'm just going to turn off the interaction markers here so that we don't have to look at those anymore. It's a little bit distracting to see all those little edge tie links, but that's okay. We can turn them on and off with a click of a button. Nice and easy. So the next step would be to go ahead and assign boundary conditions, which you can assign pressures and statics and gravities and dynamics and anything that you want to do, you can assign and fully analyze at this point. So at this point, this first demonstration is complete, and we will move on to the jacket analysis. Okay, so for demonstration number 2, we're going to jump into a jacket analysis, which is not without its complications. You can see that after I imported the geometry, I have over 1,800 parts here, and somehow this has to eventually act as one completely connected structure. And so the strategy that I'm going to take at this is build a little, solve a little, and then build a little bit more, and then connect that to the rest of the assembly and resolve it, and then keep going until eventually I have a fully validated analysis of the entire jacket. So what I'm going to do is I'm going to zoom into one of the more complicated areas here, where I have, it looks like 1, 2, 3, 4, 5, 6 different tubes connecting to another tube, and somehow that's supposed to all connect and act as one welded structure. So what I'm going to do is I'm going to drag a box around it, and I'm going to say show only, just so that we can focus on just that one section. I'm going to rotate around so that I can zoom into that location, kind of see the complicated nature of these things. Now, the first thing I'm going to do is I'm going to extract a mid-surface from these 3D solids, okay? And there are 5 different options inside of mid-surfacing. Sure, we could do things like, these are more for like machined metal and stuff like that, and we can do incremental mid-surfacing, which works really well for like injection molded plastic parts and castings and all that kind of stuff. But because these are extruded metal stock tubes, steel tubes that are welded together, we know that they're all supposed to be the exact same. And yes, we can click on them one at a time and notice what happens when we do. It'll extract the thickness and it'll show the thickness range that's associated with that. But we're going to undo that. And instead, what we're going to do is we're going to drag a box around the entire section here. And we're going to do the exact same thing where we auto extract and assign thickness. And notice that it just came up with 1, 2, 3, 4, 5 different values of thickness, which it looked like our human eyes deceived us, but the computer caught it. Nice job, Apex, by finding out that these are actually different thickness values associated with each of these metal tubes. So if we X out of mid-surface and we're just looking at the 2D surfaces, then let's move on to the next stage, which is connecting these surfaces together. So let's turn off 3D solids, and let's zoom in and kind of see how we did. Okay, so if we look at this, let's go into Vertex Edge Drag, and just like everything else inside of Apex, there's a manual method and kind of like a more automatic, quicker method of doing everything. And I'll demonstrate both of them for you right now. So the more manual method is like, let's say you want just more hands-on control of what happens when you join one edge to one surface. Well, I'm just going to drag this edge down to the destination surface. Notice the instructions that I get right at the mouse cursor and the highlighted surface before I even let go of the mouse cursor. Okay, so once I let go, notice I got a nice clean T-junction on that edge, and let's do the same thing for this guy over here. And right there we have a nice clean surface in vertices. Now, that's the more manual approach. Now, if I undo that, everything that I just did, I'm going to undo to where it's disconnected from both surfaces. There we go. Now, if I go back into Vertex Edge Drag and show those free edges, just to validate the fact that I undid every step that I just did, and Apex actually has up to 50 undos in a row, so which is it's quite nice. That's one of the niceties that we get along with having a kind of a next generation platform built on modern day computing requirements. So here we have Vertex Edge Drag, which is the more manual approach. Now, the more automatic approach, see if we had to do this kind of Vertex Edge Drag for every single surface and every single solid inside of this over 1,000 parts, almost 2,000 parts in this assembly, we would die from old age before we were finished with this analysis. So that's not the approach that we're going to take. So instead, Apex has this extend surfaces feature where we can actually use specified tolerances and just drag a box around to see what happens. Now, if I drag a box around this, around all of the parts inside of this assembly, this sub-assembly here, I'm going to zoom in and I'm going to see how I did. Hey, look at that. Instead, instead of doing every single one at a time, and it even connected these as well. Now that everything's connected, the next step would be to mesh. And we're just going to assign a surface mesh. Now, I don't know how big this part is. Let's assume that I don't want to measure it ahead of time. I'm just going to enter a mesh size of 0, and Apex is going to measure my part, and it's going to assign a mesh for me. So let me turn on the geometry in wireframe mode so that I can see the mesh, and I can see how coarse or how fine it was. So let me just go to shaded, and I can see that that's actually pretty coarse. So I'm going to measure the size of that mesh, and I'm going to do a little bit better job. So let's measure between one node and another node. It looks like 0.5 meter is the size that they assign to that automatically. So we say, all right, good job, Apex, but we're going to do better. So we're going to go back to surface mesh, and instead of 0.5, let's go to 0.25 meters. Okay, and let's just drag a box. Now we don't have to worry about deleting the mesh ahead of time. Now let's zoom in and we look at that and we say, see, that looks a little bit better. Now, but the problem is that we have to ride that fine line between good answers and taking forever to run my model, right? So a model with this mesh size for 1,800 parts is going to take a lot longer than it would be to do this analysis with a more coarse mesh. So let's just bump that up to say 0.4. Let's see what that looks like. Maybe that looks a little bit better. And sure enough, it does. Okay, so that's good enough for now. So now that this part has a mesh, it's fully connected together. Let's go ahead and analyze this and see what happens. Okay, so what do? Well, we go to this part. We say center in browser. There is my part. I'm going to say in this part, because I have a mesh, and that's the only mesh inside of my part. So I can go here and I can say place an analysis scene. Now, because this is the only part in my assembly that has a mesh assigned to it, it will go ahead and analyze this before I'm done with the entire model. And again, I'm taking the build a little and analyze a little kind of approach for this model so that I don't waste a bunch of time doing the wrong approach and just kind of incrementally move through my model. So here it says missing material assignment. And it says, all right, well, thanks, Apex, for not letting me waste all that time. So it says part 1 is missing, and 3,000 elements are missing it. So I go to my materials, and I go to my material list, and I say, okay, I just want to assign standard steel to that. And I'm just going to drag a box. And sure enough, it's going to go back to my list of offenses. And sure enough, now missing material assignment is not on my list. The only thing that's left is missing constraints and missing loads. Well, that's because by default, Apex sets it as static analysis. Now, if I want to go to a normal modes analysis, I know as a structural analyst that I can actually get away with that because my first 6 modes are going to be at 0, which is kind of like a model checkout run, right? So notice that as I change it from static to normal modes, the very last error disappears from the list, and now I can click on my little running man. Okay, so let me just go ahead and click on run. All right, now that it's done, I can go ahead and click on post-processing. And I want to validate that my model is in fact connected properly. So I turn on fringe plot and I push play, and sure enough, everything looks like it's completely connected, which looks good. It actually looks like a little insect, kind of just wiggling its way around. So I'm looking at that. Things are looking good. I'm going to bounce through a few modes, and things are good. All right, so now let's add on to this assembly, and let's move on to the rest of the structure, and follow what the rest of the workflow would be if I were to add on to this. So here I can see the section of the jacket that I've already analyzed, and let's go over to say this section as well, and let's go back to shaded geometry so I can see what what I'm doing here. So I can see that the next one is this section right here. So again, I will go ahead and say show only, but I'm going to add that to this section down here that I said show only as well. So I'm going to drag a box around that as well, and I'm going to say right click show only, and it's going to show me the assembly that I built before, and it's going to show me the section that I have not analyzed yet. So let's turn off let's turn off the surfaces and the shells, and let's go into and do the exact same thing that we did before, but we're going to go a little bit faster this time. So let's go to auto assign thickness, and we're going to drag a box around the parts that we have not done yet. And now thickness is assigned, so we're looking good. Let's go back to assigning a mesh to that. Let's turn off the solid geometry and let's turn on surfaces. There's the rest of our mid-surface. Let's turn on the shells as well, just so we can see the mid-surface, or the mesh assigned to it. We can see the part that does not have a mesh assigned to it yet. Now I can be very careful about this and mesh only the parts that I'm missing, or I could just go ahead and drag a box around everything. Now, notice that I am meshing before I connect it this time, because I just wanted to demonstrate what happens when you actually, there is no right answer in terms of the step-by-step process inside of Apex. It's very agnostic when it comes to the step-by-step process. So let's go back to extend surfaces, and it remembers the same tolerances that we had before. So I'm just going to drag a box, and I'm going to connect it up. And there you go. There is our next assembly that we are ready to analyze. So we again go to materials, and we could assign that same material to the rest of the part, and we are ready to reanalyze. So we go back to our model, and we are now ready to analyze just this substructure. Now, this same process goes through step by step by step, and eventually we get a fully completed jacket. Now, do you have to do one little subsection at a time? No. You can take bigger chunks. But the purpose of this webinar was to show you the step-by-step process that Apex walks you through at any point in time. At no point during the Apex solution time are you analyzing something, crossing your fingers, hoping that you're going to get an answer, and then you get an error. No point in time does Apex give you that workflow. So that's a thing of the past. So hopefully this second demonstration has been useful to you, and you can see how it applies to the rest of your jacket assembly or whatever large fabricated structure you may have. Okay, thank you very much. Now for this third recording, we're going to work on an assembly that would be very familiar to an oil and gas engineer or a petroleum engineer, where we have castings connected to extruded steel tubes connected together via lots of fasteners, lots of bolts, and it's all sitting on top of a welded kind of base and frame structure, if you will, that is welded together using sheet stock. Okay, so the first thing that should jump out at you is how many fasteners that are in this assembly, and that's what we're going to focus on today. But this entire model can be completed in a matter of hours, just to from initial CAD all the way through final assembly and analysis. So I've skipped the step of doing the mid-surfacing and meshing that we did in previous demonstrations, and instead we're going to focus directly on the Python scripting. Okay, so I'm going to turn off the solids, and I'm just going to turn on just the mid-surfaces to show you it to begin with, and show you that I've created this set of mid-surfaces that are 2D representations of the 3D geometry. And then I've assigned a mesh to each one of these as well, and notice that I have nice clean washer meshes around each of the holes, so that the answers, the fastener calculation answers, and the stress around those fastener holes is going to be pretty accurate. Okay, so before I engage the Python script, I just wanted to give you a little background of what the API is and how it was designed. So up here in macro, we actually have the ability to record a macro, play a macro, and then find your recently stored macros as well. But up here we also have a play, pause, record capability, And so if I hit record, notice what happens. Watch, I'll browse to just my desktop, and I'll just create a test Python script, and I will hit record. And I'm going to do this the old-fashioned way by creating a fastener by hand first, and then we'll see how it turns into the full Python script. So if I go here to connectors, and then I go right over here to flexible links, notice I have 5 other choices other than flexible links. We've got springs, dampers, combo spring damper, we've got bushings, and then we've got rigid links as well. Now each one of these pertains to certain types of fastener calculations that certain engineers want and need, but altogether it pretty much encapsulates all of them that are out there. Now here, if I go into just any arbitrary set of holes, I'm going to use this one right here. Notice that I have 2 holes that are pretty close together, and I'm going to create a fastener between each hole. Now I'm going to click on the inside edge of this. Notice it gives me a preview before I even create it. And then I click on the inside edge of hole number 2, and notice it automatically creates and lines up that fastener in between both of those holes. Okay, so here I have and it also has a nice little axis there for that fastener, so I can see the longitudinal fastener force, and then the shear force as well, so that I can make my fastener calculations when I'm fully analyzing this and looking at the answers. Now, this alone right here is a pretty nice time-saving procedure, because it saves you the need to create these spider elements on the other side. It saves you the time to create the bar or beam element in between both the center nodes. But it still doesn't address the problem of the fact that I have, hundreds of these other fastener holes in just this small little subassembly. Most oil and gas engineers would look at this and be like, oh man, I've got assemblies that I'm working on that are, 5 to 10 times as big as this, and yes, I spend days or even weeks working on these kind of models, and anything that would speed this up would be really nice. Well, notice that I'm still recording, by the way, by creating that fastener. So I'm just going to go ahead and stop. And notice if I minimize this and go to my desktop, I have this test.py Python code that if I open up, notice that it has recorded and turned it into a fully runnable Python script. Now notice that those are my connector properties that I just defined. Okay, there's my connector that attributes the connector to the geometry, and it is a fully runnable Python script right off the bat. Okay, so which is nice, because I don't have to know Python in order to utilize the Python API, which is by design. Okay, so this is nice. Let me say that one more time. You do not need to be an expert in Python in order to use the Python API. Okay, so but in order to create something where it does a little bit more detailed stuff, you kind of need to know a little bit of Python in order to figure out how it works, in order to edit this to the point where it will search for the rest of our model and really automate this Python scripting exercise. Okay, so here I'm actually going to hit undo for creating that fastener, and instead I'm going to play a macro that we have started with what I just demonstrated for you, but due to the magic of webinars, we've done a little bit of work behind the scenes, and I'm going to play a macro that we created that automatically searches the model for pairs of holes within a specified tolerance. It makes sure that there's a mesh attached to them. It figures out what the longitudinal direction of that fastener is going to be, and it assigns the material to the fastener. It connects both parts together, and it just automatically goes. So I'm going to wait for the Python to fully execute, and we will check back in when it's complete. And there you go. Now you can see that the fasteners are being created, and they're being aligned based on the longitudinal axis of both of the holes, and the center lines lining up. And just like that, we're almost done. Now once the Python executes, we're going to get a summary, and there it is. And you can see that the number of parts that were connected together, the number of holes that it searched for, and then the number of connectors right at the bottom here, it created 232 connectors in a matter of seconds here, and which was quite nice. So there you go. There is the Python API capability, and this is just scratching the surface of what the Python API is capable of. So hopefully this got your imagination running, and now you can see how to apply this to your own structures. Okay, so at this point, this is the last demonstration that I had for you guys, so we're going to switch back to PowerPoint now and close out the webinar. Okay, so thank you very much for watching the demonstrations. Hopefully they were applicable to your workflows. Just in review, what we just saw was we saw integration with Intergraph. So if you use Intergraph for your large structures, offshore structures, we have developed a script that just brings it right in, and you can analyze your finite element, you can analyze your model just lickety-split. Now, demo number 2 was the jacket analysis. So if you guys do offshore structures with large fabricated members like that, you can leverage Apex's incremental workflow where you can build a little, analyze a little, and then just move on. Again, that reaches, we demonstrated that holy grail of analysis, which is you push solve once and you get answers once. And then number 3 was automation of fasteners and scripting. So if you do pipes and fasteners together and that's causing you a lot of grief, this was just one demonstration of what the power of Apex's Python API and what it's capable of, okay? So if you like what you see, please reach out to us, request a free trial, get a demo. We would be happy to come visit you and partner with you just like we do with a lot of other companies and really kind of solve your technical problems. Again, just to review, there is no problem too difficult for MSC Software. We take it on and we are happy to do so. So please reach out when you get a second. Fred, do you have anything else to add?
Thanks, James. Yeah, really good demo. I think we're ready to open up for questions now. So you should see a Q&A window in the webinar window. Feel free to submit your questions. While we're getting started with the Q&A period, feel free to visit www.mscapex.com for more information. And through that site, as you can see on the screen here, you can request a free trial demonstration or contact MSC directly for any other questions. So with that, we'll go into a couple questions. The first one, James, I think this is for you. Is MSC Apex compatible with other tools that are heavily utilized for jackets today, like Smart3D CAD and SACS?
Oh, good question. All right. So first of all, Apex imports all the major CAD formats, okay, and the Intergraph Smart3D script. It really demonstrates the usability and that handoff between those two tools. Also, Apex outputs the Nastran bulk data file, which is the most widely accepted format and really kind of just goes into almost every platform out there. So yes, we work with almost all of the other compatible tools, and it doesn't matter. We're not going to force you to stay within the MSC family and tool suite in order to complete your analysis. We have customers today that are using Apex just as a front end, and they're doing their finish line. Like I said before during the demonstration, the finish line is exactly the same. It's just taking a 40-hour workflow and reducing it down to like 3 or 4 hours. Means a lot to them, and so they're willing to get started with Apex and finish and say things like SACS or Smart3D or Abacus or whatever you want. Good question, man.
Thanks, James. And that jacket model that you did your demonstration on, was that based on CAD or stick model?
See, that's a good one too. So when we were developing this webinar, we kind of tossed around the idea of doing a stick model and a 1D beam analysis. That is a completely acceptable workflow for that structure. Unfortunately, we just went the other way. We decided to do the 2D shell mid-surface workflow just because it gives you a little bit more detailed answers and it really showcases a lot of the tool suite. But we would be happy to set up another demo where we talk about the stick model. But just to answer your question, the jacket model that I was showing was a CAD model that came directly from Intergraph.
Thanks, James. And most of the other analysis software in use today includes code checking and alerts the user if designs do not meet the requirements. Does Apex include code checking capabilities?
Good call. So when you're talking about code checking, you're talking about basically a custom script that brings in the rules and regulations from the regulating bodies out there, whether it be ASME or shipbuilding, certifications and stuff like that. We do that as well. So we have a full API that we can build scripts and regulate and all that kind of stuff. So yes, Apex does include code checking. Good question.
Okay, the next one, I do finite element analysis on a lot of other components and assemblies. Does Apex only work on these large welded plate structures, or does it work on solids and machine parts as well?
Good one. All right, so Apex is a general purpose finite element analysis tool, right? It is not a tool for large fabricated structures. It's not a tool for automobile components. It's not a tool for airplane wings. It is a general purpose finite element analysis tool that we customize that platform for your specific needs. So it's an important handoff there. So absolutely, if you remember from the demonstration, when I went into the meshing panel, we had 5 different types of meshing there. And that basically covers, or sometimes I forget whether it was 5 or 6, but it basically encapsulates all of the types of finite element analysis that you could possibly do on all industries. So good question.
Thanks, James. The next one, and it looks like we're just about out of time, so we'll take one last question. The last one, some of the tools we are using already they're already highly automated and easy to use. What is the added benefit of Apex?
I think we somewhat addressed that in one of the earlier questions, but just to reiterate, Apex has the goal in mind that you can have the exact same finish line as you do today, right now. So if you use Sax or Smart 3D, or you use any other tool out there, the finish line is exactly the same. The thing is that if you integrate Apex into your workflow, you're looking at things like 40-hour workflows down to 4 hours, or 2 weeks worth of work down to 2 days. And that's really what you get as a trade-off of bringing in Apex to your platform. And it's completely self-taught, right? So what are you going to lose by trying this self-taught tool out? You don't have to invest a whole lot of cash. You don't even have to invest a whole lot of time in order to give it a try. So give it a shot. Who knows?
All right, thanks, James, and thank you all for watching our webinar. I think that's the end of the questions for today, and I'll hand it back to JB.
Yes, and thank you both for the questions and answers. And on behalf of Offshore Magazine and Penmore Corporation, I would like to thank Fred and James for outstanding presentations, and our sponsor, MSC Software. Again, this presentation will be archived within 24 hours and may be reached from the home page at offshore-mag.com. A reminder email message will be sent to all registrants, complete with a direct link to the archive. We thank you for joining us today and look forward to serving you with future webcasts.